What if the universe isn't just random events, but a carefully structured system with hidden patterns waiting to be found? New discoveries in cosmology are shedding light on what might have existed before the Big Bang, the event that began everything we know. Join us as we explore these mysteries, question what we thought we knew, and look into the latest discoveries about the universe. The question of what existed before the Big Bang is one of the most profound and intriguing in cosmology. The Big Bang marks the birth of our universe, but pondering what came before takes us to the very limits of scientific understanding. One leading theory suggests that the universe may have undergone a series of expansions and contractions, known as the cyclic universe theory. This idea posits that time, as we know it, may have no beginning and no end, with each cycle bringing forth a new universe. Another hypothesis worth mentioning is the concept of a multiverse. This theory suggests that our universe is just one of many that exist within a vast cosmic landscape. Each universe could have its own distinct laws of physics, dimensions, and even origins. In this view, the Big Bang could represent not a singular event in isolation, but rather the moment our specific universe emerged from an overarching multiverse. Additionally, some scientists are exploring the notion that the universe could have originated from a quantum fluctuation in a primordial state. This idea suggests that before the Big Bang, the universe existed in a superdense primordial form where conventional laws of physics break down. These quantum fluctuations might have created a critical instability, leading to the rapid expansion we now call the Big Bang. While these theories give us exciting possibilities, it's essential to remember that the truth remains elusive. The limits of our current understanding of physics, particularly at the intersection of quantum mechanics and general relativity, make it difficult to answer this foundational question definitively. As our observational technologies advance and theories evolve, we may yet uncover more about the universe's enigmatic beginnings. Modern cosmology has ignited intriguing discussions about the universe's origins, including the concept of a pre-Big Bang universe. Traditionally, the Big Bang theory sets the stage for our understanding of cosmic evolution, describing how our universe expanded from an incredibly hot and dense state approximately 13.8 billion years ago. However, scientists have theorized that the universe's story may extend beyond this singular event. One prevailing idea is rooted in the concept of quantum gravity, which suggests that before the Big Bang, the universe could have existed in a very different state. In this context, the universe may not have started from a point of nothingness, but instead transitioned from a very different realm governed by different physical laws. Some theories propose that our universe emerged from a fluctuating vacuum state or even from a previous contracting universe, hinting at a cycle of birth and rebirth in the cosmos. Furthermore, string theory, a leading candidate for a unified theory of physics, opens up fascinating possibilities regarding the nature of reality before the Big Bang. It posits that our universe is just one of many within a vast multiverse. Each universe in this multiverse could have its own set of physical laws, dimensions, and histories. This idea reshapes our understanding of reality itself, suggesting that the Big Bang was less a beginning and more of a transformation between different states of existence. Finally, cosmic inflation, the rapid expansion of the universe just after the Big Bang, also plays a crucial role in these discussions. It raises questions about what could have prompted the inflationary phase and what existed prior to it. The profound implications surrounding the pre-Big Bang universe challenge our concepts of time, space, and existence, encouraging us to consider that the universe might have an even richer and more complex narrative than we previously envisioned. Quantum mechanics, the field of physics that describes the behavior of particles at the smallest scales, significantly influences our comprehension of the universe's origins, especially in the moments preceding the Big Bang. Traditionally, our understanding of the universe's early moments relied on classical physics. However, as scientists delved deeper into these extreme conditions, they realized that classical theories fell short. Instead, quantum mechanics emerged as a critical framework for exploring the chaotic and extraordinary environment believed to exist during this period. In the world of quantum mechanics, particles can exist in multiple states simultaneously, a concept often summarized as superposition. This principle could be integral to explaining the conditions just before the Big Bang. Experts theorize that the universe may have originated from a quantum fluctuation within a vacuum state. This idea suggests that even in what seems to be empty space, energy fluctuates, potentially giving rise to the universe we now observe. Such fluctuations could have triggered the rapid expansion of space, commonly referred to as cosmic inflation. Furthermore, quantum mechanics introduces uncertainty, as described by Heisenberg's uncertainty principle. This principle indicates that the precise position and momentum of particles cannot be known simultaneously. In the context of the early universe, this uncertainty could imply a chaotic mixture of particle types and energies, paving the way for the rich tapestry of matter and energy that would eventually lead to the formation of stars, galaxies, and planets. The seemingly random nature of quantum events could provide insight into the initial conditions that set the stage for our universe. As we explore these ideas, one of the most intriguing implications is the concept of the multiverse. Some interpretations of quantum mechanics suggest the existence of multiple, perhaps infinite universes with varying properties and dimensions. This perspective challenges our singular understanding of the cosmos and invites us to contemplate what lay beyond the Big Bang. Ultimately, quantum mechanics not only acts as a bridge to comprehend our universe's inception, but also urges us to rethink the very fabric of reality itself. The concept of singularity is a fascinating aspect of cosmology, particularly when we consider the events that preceded the Big Bang. In simplest terms, a singularity represents a point in space where certain quantities, like density and temperature, become infinite. Within the framework of our universe, this idea suggests that before the Big Bang, all matter and energy were concentrated into a singularity, creating immense gravitational forces and leading to the conditions necessary for the event itself. As we look back in time towards the origins of the universe, things become increasingly complex. The Big Bang theory posits that the universe began expanding from this singular state approximately 13.8 billion years ago. But what exactly happened at that moment? Understanding singularity invites profound questions about the nature of time and space. While time, as we perceive it, began at the moment of the Big Bang, the idea of before becomes a tricky proposition. According to our best models, time may have emerged from the singularity itself, suggesting that there is no before in a conventional sense. Moreover, theoretical physics has proposed various models to explain what might have happened before this monumental event. One possibility suggests that the universe could have gone through a cycle of expansion and contraction, hinting at a multiversal scenario where singularities can mark entrances into different regions of time and space. Another intriguing perspective involves quantum fluctuations, which imply that the very fabric of space-time might have experienced chaotic behaviors leading up to the Big Bang, potentially resulting in the birth of our universe. Though these ideas remain speculative, they inspire continued exploration into the complexities of existence itself. Singularities challenge our understanding of the cosmos and the laws of physics as we know them. They compel us to think deeply about the origins of everything we observe today. As scientists develop new technologies and methods to probe the universe's early moments, the mystery of what lies beyond that singularity continues to fuel scientific inquiry and philosophical contemplation alike. Physicists often turn to mathematical models as essential tools for exploring the mysterious conditions that may have existed prior to the Big Bang. These models allow scientists to delve into concepts that go beyond direct physical observation, making it possible to form hypotheses about a time when the universe was vastly different from what we know today. The pre-Big Bang era is characterized by extreme conditions and unique states of matter and energy, which can be puzzling to comprehend without these abstract tools. One prominent example is string theory, which proposes that fundamental particles are not merely point-like objects, but rather tiny, vibrating strands of energy. In this framework, physicists craft intricate mathematical formulations to analyze how these strings could behave in environments where traditional laws of physics might not apply. This approach provides a way to suggest what matter and forces might have interacted like before the universe began to expand, offering insights into the very fabric of reality. Another significant area of research involves the concept of quantum gravity, attempting to unify general relativity and quantum mechanics. Models that incorporate elements of both theories enable physicists to investigate how gravity might function at singularities, such as those believed to exist at the beginning of the universe. These models reveal how space and time could behave differently in extreme conditions, suggesting that our understanding of these concepts may need radical revision when considering the universe's earliest moments. Lastly, cosmological simulations use powerful mathematics to create virtual universes, allowing scientists to examine how various initial conditions could lead to the universe we observe today. By tweaking parameters and observing the results, physicists can gain insights into potential scenarios of cosmic evolution, including those that might have characterized the pre-Big Bang epoch. This blend of mathematics and cosmology enriches our understanding and keeps the quest for knowledge alive in the ever-expanding realm of the universe's history. In the context of pre-Big Bang conditions, scientists grapple with the very concept of time itself. Traditionally, time is understood as a measure of change, seconds ticking by, events unfolding in a sequence. However, before the Big Bang, that familiar notion of time begins to unravel. The prevailing theories suggest that time as we know it did not exist in the conventional sense. Instead, it was bound up with processes that we still struggle to fully comprehend. To delve deeper, it's crucial to consider the nature of the universe before the Big Bang. Some researchers propose that at this point, the universe was compressed into an incredibly hot and dense state. In this scenario, the attributes of space and time were intertwined, forming what we call space-time. This means that without the universe as we perceive it today, expanding and cooling, there may have been no time. The emergence of time could very well be linked to the moment when the universe began to expand, marking the beginning of both space and temporal order. Furthermore, scientists explore concepts like quantum gravity to understand these early conditions. These theories suggest that the conventional framework of time breaks down at quantum scales. Instead of moving through the fabric of time in a linear fashion, the dynamics of the early universe could involve a more complex interplay of events that don't align with our typical understanding of past, present, or future. This opens up fascinating ideas about time being a property that emerged with the universe itself. Ultimately, the exploration of time in the pre-Big Bang context challenges us to rethink not just the nature of time, but also our place in the cosmos. As scientists continue to investigate these mysteries, they push the boundaries of our knowledge, inviting us to contemplate the very essence of existence and the universe's beginnings. Each insight adds a layer to our understanding of how everything, space, time, and life, interconnects in this vast tapestry we call reality. The Planck era is a critical period in the history of our universe, marking the very beginning of time and space as we understand them. This era lasted from 0 seconds to about 10 to the negative 43 seconds after the Big Bang. During this minuscule fraction of time, the universe was unimaginably small, hot, and dense. The laws of physics as we know them break down under such extreme conditions, making the Planck era a frontier of scientific exploration and speculation. Understanding the Planck era helps scientists delve into the fundamental forces of nature. At this time, gravitational, electromagnetic, and nuclear forces were indistinguishable due to the extreme energy levels present. This suggests that these forces may have originated from a single, unified force. By investigating this early stage of the universe, researchers hope to uncover insights into how these forces separated and evolved into the fundamental interactions we observe today. This focus on the Planck era also raises profound questions about the nature of the universe. Questions arise about what existed before the Big Bang and what initiated this explosive expansion. Theoretical physicists employ models rooted in quantum mechanics and general relativity, trying to piece together a coherent narrative of our universe's origins. Concepts such as quantum gravity are vital in these discussions, as they aim to bridge the gap between particle physics and cosmology. As we explore the mysteries of the Planck era, we encounter more than just scientific inquiry. We delve into the essence of existence itself. This period invites us to consider our place in the universe, encouraging a deeper understanding of the cosmos's birth and development. Ultimately, the significance of the Planck era lies not only in what it reveals about the early universe, but also in how it challenges our perceptions of reality and the very fabric of time and space. The concept of the Big Bang is often viewed as the very beginning of both space and time. However, recent theories exploring pre-Big Bang events introduce a provocative notion that the cosmos may have existed in some form even before this monumental event. This challenges the traditional view by suggesting that both space and time are far more elastic and complex than once imagined. Instead of a singular starting point, it opens the door to various interpretations of how the universe might have been structured or how it could have functioned prior to that first spark. One intriguing area of research delves into the idea of a cyclic universe. In this model, the universe undergoes infinite cycles of expansion and collapse. Each Big Bang is not the absolute beginning, but rather a transition point from a previous state. This posits that instead of a linear progression, time may be more like a circular path, leading to the possibility that events preceding each Big Bang could influence subsequent ones. This perspective fundamentally alters how we think about causality, as actions taken in one cycle could echo into the next. Another interesting line of inquiry involves quantum mechanics and the nature of reality itself. Some physicists theorize that before the Big Bang, the universe may have existed in a state governed by quantum fluctuations, where the very concepts of space and time as we understand them were not yet applicable. In this realm, particles could be both here and there all at once. This notion challenges the classical understanding that our universe operates under fixed laws of time and space, suggesting instead that reality at its most fundamental level may be inherently unpredictable and interconnected. These theories are not just academic musings. They invite us to rethink what we know about existence itself. If the universe is indeed a tapestry woven through both time and space that extends far beyond the Big Bang, the implications stretch into the very fabric of how we perceive our reality. They urge us to embrace the mysteries that lie beyond traditional cosmological ideas and consider that what we label as beginnings and endings might be moments in an ongoing and magnificent story of cosmic evolution. The concept of time as we understand it has deep connections to the birth of the universe itself, particularly with the event known as the Big Bang. Deep within the scientific community, there is a compelling argument that time, in its familiar form, may not have existed prior to this crucial moment. To unpack this idea, we need to look at both theoretical implications and empirical evidence that supports it. According to our current understanding of physics, particularly the theory of relativity, time is interwoven with space to form what we refer to as space-time. Before the Big Bang, it is believed that the universe was in an incredibly hot and dense state where the very fabric of space-time emerged. In this context, any discussion of before the Big Bang becomes problematic, as time itself may not have had a framework in which to exist. Thus, the Big Bang represents not just a dramatic expansion of the universe, but also the inception of time itself. Further bolstering this idea are models stemming from quantum gravity and string theory, which suggest that at the fundamental level, the universe might behave quite differently than our everyday experiences lead us to expect. These models propose scenarios where concepts of time break down. In a way, this mirrors the notion of the singularity that marks the Big Bang, a point where our conventional understanding of physics ceases to apply. Additionally, observational evidence, such as the cosmic microwave background radiation, reinforces the idea that our universe had a tangible beginning marked by the Big Bang. This remnant radiation is a snapshot of the early universe, providing clues about the conditions that existed shortly after its inception and suggesting a definite point in time from which all subsequent moments flow. Therefore, while the question of what existed before the Big Bang may seem intuitive, current scientific perspectives indicate that our very notion of time itself may have been born along with the universe. The concept of space-time, as we understand it today, undergoes a fascinating transformation when we delve into the pre-Big Bang universe. Traditionally, we think of space-time as a fabric that intertwines the three dimensions of space with time itself. However, the conditions before the Big Bang challenge this understanding profoundly. Before the event that initiated our universe, It's hypothesized that space-time as we know it did not even exist in a recognizable form, making discussions around it both intriguing and complicated. In the moments leading up to the Big Bang, many scientists suggest that the universe was in an extremely hot, dense state. This singularity, in which temperature and density tend toward infinity, poses questions to our existing models of physics. The mathematics of general relativity break down in such extreme conditions, indicating that our conventional understanding of space-time fails. Instead of a structured timeline that unfolds within an established spatial context, we might have to reconsider the very fabric that holds time and space together. Theories such as quantum gravity explore the very nature of space-time at these extraordinary scales. Some propose that space-time may be more fluid and dynamic than we realize, potentially stretching or warping in ways that we have yet to comprehend. In this context, space-time could have been in a state of potentiality, not quite developed as we experience it today. Thus, the evolution of space-time becomes intricately linked to processes that led to the creation of our universe, presenting a canvas of possibility before our reality took form. As we continue to explore these concepts, it's becoming increasingly evident that the narrative of the pre-Big Bang universe may shift our fundamental understanding of physics altogether. With more advanced theories and potential discoveries awaiting us, the mystery of what existed before space-time adds yet another layer of intrigue to the ongoing journey of unraveling the universe's deepest secrets. Scientists are embarking on a quest not just to find answers, but to reshape the very questions we ask about existence itself. The cyclic model presents a fascinating perspective on the nature of time and space, proposing that our universe undergoes endless cycles of expansion and contraction. According to this view, instead of a singular beginning like the Big Bang, the universe experiences a series of these cosmic events. After reaching a point of maximum expansion, the universe, instead of fading into nothingness, contracts back to a state of incredibly high density, ultimately leading to another Big Bang. This cyclical process suggests that time and space are not finite, but are perpetually renewed. One of the most intriguing implications of this model is the idea of continuity. It challenges the traditional notion of a defined beginning and end, suggesting that time may be infinite in a sense that it continually unfolds across these cycles. Each cycle could represent a unique iteration of the universe, potentially evolving with different physical properties or laws. This viewpoint leads to philosophical questions about the nature of existence and reality as we know it, suggesting that our current understanding of time might be just one chapter in an endless story. Moreover, the cyclic model posits that the universe could preserve certain features or structures over these cycles, such as the patterns of cosmic background radiation and the distribution of galaxies. This accumulation of cosmic memory hints at a deeper interplay between the past and the future, where each cycle informs the next. Essentially, it offers a vision where the universe is seen as a dynamic, ever-repeating tapestry woven together by the threads of time and space. The cyclic model invites us to reconsider fundamental concepts of time and space. Instead of a linear progression from the Big Bang to a finale, it suggests a rhythmic dance of cosmic evolution that is both eternal and transformative. This perspective not only reshapes our understanding of cosmology, but also sparks intriguing considerations about the destiny of our universe and the nature of reality itself. Cosmic inflation theory revolutionizes our understanding of the universe's infancy by proposing a dramatic expansion of space during the first moments after the Big Bang. This theory suggests that within a fraction of a second, the universe expanded exponentially, growing from smaller than an atom to the size of a solar system. This incredibly rapid expansion smooths out any irregularities, leading to the uniformity we observe in the cosmic microwave background radiation today. Before inflation was proposed, the Big Bang model could not fully explain the vastness and homogeneity of the universe. Cosmic inflation provides a framework for understanding how our universe transitioned from an incredibly dense and hot state into the cooler, expanding cosmos we see now. It bridges the gap between quantum physics and cosmology, suggesting that quantum fluctuations during inflation could be the seeds of all the large-scale structures we observe, like galaxies and clusters. Moreover, this theory opens up intriguing possibilities about what might have existed before the Big Bang, with some researchers proposing that our universe could be one of many in a multiverse, a concept where an infinite number of universes exist, each with different properties. These ideas challenge our traditional notions of time and space, suggesting that the fabric of reality may be woven with threads of potential realities. By exploring cosmic inflation, scientists gain deeper insights into the fundamental laws governing the universe and the history of its creation. This perspective not only enriches our understanding of the universe's early moments, but also encourages further research into the nature of existence itself, continually feeding our curiosity about what came before the seemingly inconceivable moment we call the Big Bang. Cosmic inflation is a groundbreaking theory that reshapes our understanding of the universe's beginnings. This concept suggests that shortly after the Big Bang, the universe experienced a rapid expansion, growing exponentially in size within fractions of a second. This period of inflation could have implications for what happened before the Big Bang, raising fascinating questions about the nature of the cosmos. Before the advent of cosmic inflation, many scientists assumed the universe started in a hot, dense state with no prior history. However, inflation introduces the possibility that our universe is just a small part of a much larger multiverse. This multiverse concept proposes that other regions of space could exist beyond our observable universe, potentially leading to different laws of physics. This radical idea expands our thinking about what the universe could be and suggests that multiple Big Bang events may have occurred in this grand cosmic landscape. One of the most intriguing aspects of inflation is its ability to solve several enigmas of the Big Bang theory. For instance, it addresses the uniformity of the cosmic microwave background radiation. This radiation is remarkably consistent across vast distances, despite the observable universe being filled with variations. Inflation proposes that the universe was once in a state of near-perfect uniformity, which was then stretched to the size of the observable universe, leaving behind this smooth background. Additionally, cosmic inflation impacts our understanding of the structure of the universe. It suggests that tiny fluctuations during this rapid expansion serve as the seeds for galaxies and large-scale structures we observe today. As inflationary periods influence the distribution of matter, they weave the intricate tapestry of the cosmos we continue to explore. Thus, cosmic inflation not only deepens our understanding of the Big Bang, but also invites us to reconsider the nature and origins of everything we see in our universe. Scientists employ a variety of innovative methods to test the validity of inflationary models, which explain the rapid expansion of the universe just after the Big Bang. One of the primary approaches involves the analysis of the cosmic microwave background, or CMB. This relic radiation from the early universe serves as a snapshot of the cosmos when it was just a mere fraction of a second old. By examining tiny fluctuations in temperature and density in the CMB, scientists can infer details about the physics of inflation, including its duration and the energy scale involved. In addition to the CMB, researchers also look for specific patterns of gravitational waves, which are ripples in spacetime caused by accelerating masses. Inflationary models predict that such waves should exist and that their signatures can be faintly detected. By utilizing advanced instruments, like the Laser Interferometer Gravitational Wave Observatory, scientists are on the lookout for these gravitational signatures that would provide strong evidence supporting inflationary theory. Furthermore, scientists conduct simulations of large-scale structure formation in the universe. These simulations help them observe how galaxies and cosmic structures would evolve under different inflationary scenarios. By comparing the predicted distributions of galaxies and clusters to those observed in surveys, researchers can assess the accuracy of various inflationary models. A match between simulation and observation can lend significant weight to a given model of inflation. In recent years, new observational missions, such as the Planck satellite, have greatly enhanced our understanding by providing high-resolution maps of the CMB. As data continues to accumulate, our comprehension of the early universe deepens, bringing with it a remarkable glimpse into how inflation might have shaped our reality. Through this multifaceted approach, scientists are working tirelessly to validate and refine the intricate theories surrounding the universe's explosive beginnings. Inflationary theories play a crucial role in understanding the large-scale structure of the universe. At the core of these theories lies the concept that, during the very early moments after the Big Bang, the universe underwent an exponential expansion. This rapid stretching of space helped to resolve some of the significant challenges posed by the observed uniformity and smoothness of the cosmos, particularly the principles of homogeneity and isotropy. Homogeneity refers to the idea that the universe looks the same at every point when viewed on a large scale. Isotropy means that the universe appears the same in all directions. These properties are evident in the cosmic microwave background radiation, where tiny fluctuations exist but are remarkably uniform when viewed at a grand scale. Multiverse theories offer intriguing perspectives on what might have existed before the Big Bang, challenging our traditional understanding of the universe's origin. According to these theories, our universe is just one of many, possibly an infinite number, existing alongside each other in a vast multiverse. This idea opens up a realm of possibilities about the state of reality before the explosive event that gave rise to space and time as we know it. One prominent concept within multiverse theories is the idea that different universes may arise from various physical laws or conditions. This means that while our universe is characterized by specific constants and properties, there could be universes with entirely different characteristics. Some models suggest these universes might have emerged from a parent universe, undergoing a process of cosmic inflation or transformations that created branching realities. In this scenario, rather than a singular beginning, the multiverse frames existence as a dynamic interplay of many beginnings, some of which may precede our own. Moreover, certain theoretical frameworks propose that time itself might not have always existed as we understand it. Before the Big Bang, in this view, there could be a state of existence that is timeless or characterized by entirely different dimensions. For instance, some physicists suggest the possibility of a cyclical universe where the Big Bang is simply one transition in an endless series of expansions and contractions. This perspective allows for the consideration that prior states or forms of reality existed independent of our traditional notions of beginning and end. As scientific understanding evolves, multiverse theories challenge us to rethink our universe's origins and raise profound philosophical questions about existence. They inspire both awe and curiosity, moving our inquiries beyond the singular event of the Big Bang to a broader landscape of cosmic possibilities. In this vast expanse, the boundaries of our understanding stretch and shift, inviting us to explore not just what exists within our universe, but the nature of reality itself across potentially limitless dimensions. The concept of the multiverse opens up a fascinating array of ideas, especially when we delve into pre-Big Bang scenarios. One prominent theory suggests that rather than being a singular event, our universe is just one of many that have emerged from an infinite sea of other universes. This idea can be traced back to the inflationary model of the early universe, which posits that rapid expansion occurred shortly after the Big Bang. According to this view, different regions of space underwent inflation in varying ways, leading to pockets of space that became distinct universes, each with its own unique properties. Another intriguing multiverse theory is the cyclic model. This hypothesis proposes that our universe undergoes endless cycles of expansion and contraction. In this scenario, each cycle ends with a big crunch, followed by a new Big Bang, giving rise to a new universe. This continual rebirth offers a rich tapestry of possibilities and allows for the exit of various physical laws and constants that could differ across cycles, resulting in a vast multiverse landscape where each universe has its own distinct characteristics. The landscape multiverse further expands these ideas. It arises from string theory, which suggests that fundamental particles are made up of tiny vibrating strings. String theory allows for a multitude of ways these strings can vibrate, each leading to different physical laws and universes. Within this framework, there are potentially 10,000 or even more unique combinations that describe different versions of reality. Some of these universes may have conditions that allow for life, while others might operate under completely alien physical laws. Lastly, we have the concept of the quantum multiverse, which springs from quantum mechanics. In this view, Every time a quantum event can have multiple outcomes, the universe splits into different branches, with each outcome occurring in its own universe. This means countless versions of reality coexist, mirroring the scenarios in which all possible outcomes play out. When considering pre-Big Bang scenarios, these theories invoke the idea that even before our universe came into being, there might have been a wide array of alternate existences already unfolding. Each of these multiverse theories offers a unique lens through which to explore our cosmic origins, reminding us of the vast, interconnected possibilities of existence. The concept of the multiverse is one of the most tantalizing ideas in modern cosmology. It suggests that our universe, with its vast galaxies, stars, and planets, might be just one of many universes existing simultaneously. This possibility stems from various theoretical frameworks, primarily stemming from quantum mechanics and cosmic inflation. Scientists have long sought to understand why our universe has the specific conditions that allow life. The multiverse theory offers a compelling explanation. If many universes exist, it is not surprising that at least one of them would have the right conditions for life. One of the key ideas supporting the multiverse hypothesis comes from cosmic inflation, a theory that describes the rapid expansion of the universe just after the Big Bang. This inflationary phase suggests that different regions of space could have expanded differently, leading to pocket universes that have distinct properties. These bubble universes could have varying laws of physics, constants, and dimensions, resulting in a remarkable diversity of universes, some of which could support life and others that are utterly uninhabitable. Another angle comes from quantum mechanics. The many worlds interpretation postulates that every quantum event creates a branching of the universe into multiple realities, where every possible outcome is realized in its own separate universe. This interpretation challenges the classical view of a single reality, opening up the realm of possibilities that there are countless universes, all arising from the fundamental principles of quantum physics. While the multiverse remains a speculative idea and presents significant challenges in terms of empirical testing, it inspires scientists and enthusiasts alike. It challenges our understanding of existence itself and raises profound questions about the nature of reality. As researchers continue to explore the cosmos, the notion of our universe being part of a vast multiverse keeps us questioning and pondering what else might be out there beyond the observable limits of space and time. The concept of a multiverse suggests that our universe is just one of many that exist, potentially with different laws of physics and constants. While the idea may sound like something from science fiction, intriguing evidence could hint at the existence of multiple universes, even before the Big Bang. One significant piece of evidence comes from the phenomenon of cosmic inflation. This theory proposes that just after the Big Bang, the universe underwent an exponential expansion. Some scientists speculate that this inflationary process could occur repeatedly, generating bubbles that become separate universes. The remnants of such inflation might leave behind patterns in the cosmic microwave background, the faint glow left over from the Big Bang. If we could identify anomalies or unusual patterns that cannot be explained by standard cosmology, it could suggest interactions with other universes. Further support for the multiverse idea stems from string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. This framework allows for enormous variations in physical laws, meaning our universe's properties could be just one of countless outcomes in a vast landscape of possibilities. The mathematical framework underlying string theory produces models with many dimensions and variations, potentially creating an environment where different universes could coexist. Context from quantum mechanics also fuels the multiverse hypothesis. The theory of quantum mechanics suggests that particles do not have definite states until measured. This has led to interpretations that propose entire realities branch out with every quantum event, leading to an infinite number of parallel worlds. While speculative, this idea resonates with the notion that universes could emerge from decisions or events that happen at the cosmic scale, extending the timeline of existence back to a period before the Big Bang itself. While concrete evidence for a multiverse remains elusive, theories like cosmic inflation, string theory, and quantum mechanics provide tantalizing possibilities that could illuminate the existence of multiple universes, possibly even prior to our own universe that we recognize today. The concept of a multiverse presents a fascinating framework for understanding the origins of our universe and its early moments. Traditionally, many have pondered the question of how our universe began, often leading to the idea of a singular Big Bang event. In contrast, the multiverse theory suggests that what we perceive as our universe may be just one of many, each emerging under its own distinct conditions. This perspective challenges the notion of a singular beginning, inviting us to consider multiple cosmic histories. In this multiverse scenario, universes can vary dramatically in their physical laws, constants, and even dimensions. Some may emerge from the remnants of previous universes that collapsed, while others could manifest from quantum fluctuations in a more significant cosmic landscape. This means that the beginning of our universe might not be a unique event, but rather part of an ongoing cycle of creation, expansion, and potential rebirth within a broader multiversal framework. Furthermore, the multiverse concept can help to address some of the perplexing features of our own universe, such as its remarkable fine-tuning for life. With an infinite or vast collection of universes, each with different properties, it becomes less surprising that at least one universe, like ours, would develop conditions conducive to life. In this light, rather than being an anomaly, our universe could be just one of countless realms, each representing a different outcome in the cosmic lottery. As we delve deeper into these ideas, the multiverse not only enriches our understanding of cosmic origins, but also ignites our curiosity about existence itself. It pushes the boundaries of traditional cosmology, inspiring scientists and thinkers to explore the fundamental questions of reality, existence, and the nature of the cosmos on a grand scale. This entanglement of possibilities challenges our definitions of beginning and universe, leading us to contemplate an infinite tapestry of realities, each with its own story to tell. Quantum gravity is a fascinating area of theoretical physics that seeks to merge the principles of quantum mechanics with the force of gravity. This effort becomes particularly intriguing when we consider frameworks that describe a pre-Big Bang universe. Quantum gravity suggests that at the smallest scales, the fabric of space-time is not smooth and continuous, but rather discrete and subject to the uncertainty dictated by quantum mechanics. In models of a pre-Big Bang scenario, quantum gravity plays a critical role in understanding what might have existed before our universe began to expand nearly 14 billion years ago. Traditional theories of gravity, grounded in general relativity, break down under extreme conditions, such as those thought to exist at the very beginning of time. Quantum gravity proposes that all particles and forces, including gravity, manifest through a fundamental quantum field. This allows for the possibility that the universe could have undergone a different phase or state before the Big Bang, rather than being an absolute beginning. Some models, like the cyclic universe scenario, incorporate elements of quantum gravity to suggest that the universe goes through infinite cycles of expansion and contraction. In this view, the Big Bang is not a singular event, but rather a transitional phase. The quantum fluctuations during this contraction could lead to a new Big Bang, allowing for a continuous series of cosmic rebirths. Such considerations challenge our conventional notions of time and space, inviting us to think about the universe in a way that defies simple linear progression. Moreover, quantum gravity may offer insights into some of the fundamental properties of the universe. For example, the concepts of entropy and causality take on new dimensions in a pre-Big Bang context. Understanding how space-time behaves at these quantum levels could reveal deep connections to the laws governing the universe, emphasizing the interplay between the microscopic and the cosmic. As we delve deeper into this realm of theoretical physics, we are continually reminded of how much remains to be discovered about the origins of our universe and the profound complexities underlying its existence. String theory is a captivating framework in theoretical physics that aims to reconcile quantum mechanics and general relativity. Its implications extend beyond our observable universe, sparking intriguing possibilities about conditions and realities that may have existed prior to the Big Bang. Essentially, string theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings of energy. These strings can exist in multiple dimensions, some of which remain beyond our everyday experience. In the context of the universe before the Big Bang, string theory introduces the concept of a pre-Big Bang scenario. It suggests that the structures of space and time may have undergone significant transformations, having originated from a state of higher dimensional space known as the string landscape. In this model, the fluctuations and interactions of strings could have paved the way for the rapid expansion that we recognize as the Big Bang. This thinking challenges traditional ideas, proposing that our universe might be just one of many phases within a more extensive and complex multiverse. Moreover, string theory allows scientists to consider how the laws of physics themselves may have been different in the very early universe, or even non-existent as we define them today. In this framework, the forces and particles that define our realities could emerge from the dynamics of strings interacting in higher dimensional spaces. This opens up avenues to explore what time could have meant in a pre-Big Bang universe and how our understanding of causality might need to evolve. While the specifics of the universe before the Big Bang remain largely speculative, string theory offers a tantalizing glimpse into potential origins and an underlying unity in the cosmos. By examining these ideas, scientists hope to unravel the mysteries that lie at the edges of our understanding, pushing the boundaries of what we know about the universe's history and the fundamental nature of reality itself. String theory, a leading candidate in the search for a unified theory of physics, presents revolutionary ideas that significantly challenge our traditional cosmological concepts. At its core, string theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in various ways, giving rise to the different types of particles we observe. This concept not only alters our understanding of particle physics, but also leads to profound implications for the structure of the cosmos itself. One major challenge posed by string theory is the idea of extra dimensions. While traditional cosmology typically operates within the familiar 3 dimensions of space and one of time, string theory suggests that there are additional dimensions, potentially as many as 10 or 11. These extra dimensions are compact and not directly observable at the everyday scale. However, their implications ripple through the fabric of space and time, influencing the fundamental forces and the way gravity operates, potentially explaining phenomena that standard models cannot adequately address. Moreover, string theory introduces the notion of a multiverse, a collection of multiple, possibly infinite universes, each with its own unique laws of physics. This challenges the traditional perspective that our universe is the only one that exists. Instead, it opens the door to a vast array of possibilities where different universes may have different constants and fundamental forces. Such a radical shift encourages cosmologists to explore the implications of how our universe fits into this broader multiverse framework, raising questions about the nature of reality itself. Lastly, the mathematical complexities inherent in string theory often lead to a more speculative approach to cosmology. While traditional models may focus on observable phenomena and empirical data, string theory's abstract nature can sometimes lead to conclusions that are not easily testable with current technology. This clash between theoretical elegance and empirical evidence not only challenges the foundations of cosmological understanding, but also encourages ongoing dialogue and exploration within the scientific community. As our observational technologies advance, we may uncover new ways to test these intriguing ideas, further shaping our understanding of the universe. String theory posits that the fundamental building blocks of the universe are tiny vibrating strings rather than point-like particles. This idea leads to intriguing predictions about conditions that may have existed before the Big Bang, suggesting a pre-Big Bang phase featuring extra dimensions and unique energy states. But how could we find evidence to support these predictions? One of the key tenets of string theory is its ability to unify gravity with the other fundamental forces of nature. A compelling line of evidence would involve the detection of gravitational waves that correspond to the conditions of the early universe, potentially revealing echoes from a pre-Big Bang state. Scientists have been tirelessly exploring cosmic microwave background radiation, the afterglow of the Big Bang itself, for anomalies or patterns that might imply interactions with extra dimensions, as string theory suggests. Additionally, strings could produce unique particles, often referred to as superstrings, that might reveal themselves in high-energy phenomena. If particle accelerators like the Large Hadron Collider were to detect signatures of these elusive particles, it could bolster string theory's claims about a more complex, layered reality than currently understood. These discoveries would offer tangible proof that the universe may not be a singular event, but rather part of a more intricate, multidimensional tapestry. Furthermore, understanding anomalies in cosmic inflation could also provide vital clues. If models of inflation indicate a connection to string theory's higher dimensional framework, scientists could reverse engineer events that transpired before the Big Bang. Identifying such a link could transform our understanding of the universe's origins and lend credibility to string theory's expansive vision of reality. String theory stands at the intersection of two monumental pillars of modern physics: quantum mechanics and general relativity. At the heart of this theoretical framework is the idea that the fundamental building blocks of the universe are not tiny particles, but rather one-dimensional strings. These strings can vibrate at different frequencies, and their various modes of vibration correspond to different particles. This innovative perspective offers a potential reconciliation between the behaviors described by quantum mechanics and the geometric nature of spacetime outlined in general relativity. In a pre-Big Bang universe, the conditions are believed to be vastly different from those we experience today. Traditional theories predict singularities, points of infinite density, where the laws of physics break down. String theory, however, provides a smoother transition through these early moments. It suggests that the very fabric of spacetime could be shaped and influenced by these vibrating strings, allowing for a universe that is more interconnected and cohesive than previously thought. Before the Big Bang, the universe could have existed in a kind of stringy state where quantum fluctuations shaped the cosmic landscape. Furthermore, string theory incorporates additional dimensions beyond the familiar three. While our common experience tells us about 3 dimensions of space and 1 of time, string theory posits up to 9 spatial dimensions that are compacted and not directly observable. These extra dimensions play a crucial role in unifying the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces, bridging the gap between the quantum realm and the macroscopic world governed by general relativity. Ultimately, the beauty of string theory lies not just in its theoretical elegance, but also in its potential to describe a network of interactions that predates the classical understanding of time and space. Scientists are still exploring the implications of this theory, seeking both experimental evidence and insights that could illuminate the conditions leading to the Big Bang. As we continue to unravel the cosmos, string theory offers a captivating glimpse into the universe's intricate web, suggesting that the very essence of reality may be woven together in ways we are only beginning to understand. Black holes are among the most enigmatic objects in the universe, wielding incredible gravitational power that warps space and time. Their study offers profound insights into the nature of the cosmos. Some scientists propose that black holes might hold clues about conditions before the Big Bang, the event that marked the birth of our universe approximately 13.8 billion years ago. One fascinating theory suggests that black holes could be gateways to other universes or dimensions. According to this view, a black hole forms when a massive star collapses under its own gravity, creating a singularity, a point where density and gravitational forces become infinite. Some theorists speculate that these singularities could be connected to what came before our universe, potentially acting as conduits for matter and energy from previous cosmic epochs. Moreover, studying the radiation emitted by black holes known as Hawking radiation leads to intriguing implications about the information paradox and the nature of space-time itself. This concept challenges traditional views of how information is lost when objects fall into black holes. If it is possible for information to escape or be transformed, this could provide insights into the state of the universe before the Big Bang, suggesting a continuity or cyclical nature of cosmic evolution rather than a strict beginning with the Big Bang. While black holes themselves do not offer direct evidence of the universe's pre-Big Bang state, they underscore the limits of our understanding and ignite curiosity about the framework of existence. As researchers continue to explore the mystery surrounding these cosmic giants, They bolster the case for new theories that could potentially bridge the gap between current models of cosmology and the mysteries that lie beyond our observable universe. White holes, the theoretical opposites of black holes, present fascinating scenarios in our attempts to understand the origins of the universe. While black holes are known for their ability to pull everything inward, white holes would hypothetically expel matter, energy, and information. This unique property has led some scientists to speculate about their role in cosmic events, especially in relation to the birth of our universe. One intriguing scenario posits that white holes could be linked to the Big Bang. According to this idea, our universe may have emerged from a white hole that ejected energy and matter into a previously existing void. Such a process would offer a novel perspective on the question of what preceded the Big Bang. If white holes exist, they might provide a mechanism for the universe's birth, suggesting that they could spit out the very building blocks of galaxies, stars, and planets. Another possibility connects white holes to black holes through a theory known as wormholes. Some researchers speculate that a black hole could be connected to a white hole via a tunnel in space-time, known as a wormhole. In this model, matter that falls into a black hole might be ejected from a white hole in another location, or possibly even another universe. This interconnectedness could open up fascinating questions about the cyclic nature of the universe, where matter is continuously transformed and redistributed. While these concepts remain speculative and lack empirical evidence, they ignite our imagination about the cosmos. The nature of white holes challenges our understanding of physics and raises profound questions about the origins and fate of our universe. As scientists continue to explore these possibilities, they push the boundaries of cosmology, reminding us of the mysteries that still lie beyond our current comprehension. Black holes, those enigmatic regions of space where gravity is so intense that not even light can escape, have profound implications for our understanding of the universe. They challenge our traditional notions of space, time, and gravity. Recent research suggests that black holes could be more than just cosmic vacuum cleaners. They might also provide a glimpse into pre-Big Bang realities. This idea stems from the peculiarities of black hole singularities, the points at their centers where density becomes infinite. One intriguing theory is that black holes may serve as gateways or connections to other universes or dimensions. When matter collapses into a black hole, it raises questions about what happens within that singularity. If we consider what might emerge on the other side of a black hole, we could be looking at an entirely separate universe or a different state of reality altogether. This concept is not just science fiction. Some physicists propose that our own universe could have originated from the collapse of an earlier universe into a black hole, suggesting a cyclical model of cosmic rebirth. Equally thought-provoking is the idea that studying the quantum effects near black holes might reveal clues about conditions before the Big Bang. The merger of quantum mechanics and general relativity is a key challenge in modern physics. By examining the behavior of matter and energy under extreme gravitational forces, scientists hope to uncover insights about the very fabric of space-time and what might have existed before the universe as we know it took shape. Thus, black holes are not mere cosmic oddities, but rather potentially vital components in unraveling the mysteries of the universe's origins. They encourage us to ponder profound questions about existence, the nature of reality, and the possibilities that lie beyond our observable universe. As we continue to delve into the intricate dance of gravity and space-time, we edge closer to understanding how black holes could illuminate the hidden narratives of pre-Big Bang realities. The study of Hawking radiation offers intriguing insights into the fabric of our universe, particularly regarding the conditions that may have existed before the Big Bang. Proposed by the renowned physicist Stephen Hawking in 1974, this form of radiation emerges from black holes due to quantum effects near the event horizon. Essentially, it reveals that black holes can emit radiation and lose mass, eventually leading to their evaporation. This concept challenges long-held notions of black holes as entities that solely consume matter and energy, suggesting instead that they play an active role in cosmic processes. Understanding Hawking radiation goes beyond the fate of black holes. It also hints at the very nature of space and time. As we consider the state of the universe before the Big Bang, questions arise about what sort of matter and energy existed and how quantum mechanics might have influenced these primordial conditions. Hawking's theory bridges concepts of thermodynamics and quantum physics, suggesting a dynamic early universe, potentially rife with fluctuations that could have set the stage for the Big Bang itself. Moreover, Hawking radiation implicates a larger relationship between gravity and quantum mechanics, a relationship that we still strive to fully understand. The radiation suggests that the universe could possess properties of a quantum field, which might have existed in a chaotic state before the expansion of the cosmos. This era could have seen a mix of particles and antiparticles, dancing in a quantum ballet that would eventually give rise to the universe as we know it. In pondering the implications of Hawking radiation for pre-Big Bang conditions,